Alright, so now we're going to do an example of how to actually do an analysis of variance test using some example data and going through all of our hypothesis testing steps. So the data I have written here is from 3 samples, so imagine you're taking some small samples from urban, suburban, and rural areas, and you're asking everybody, oops, I should say 10, not 100. You're asking everybody on a scale from 1 to 10 how fair they think the police are, where 10 would be the most fair and 1 would be the least fair. And so in this example data, we had 19 people in our urban sample with an average of 4 and a standard deviation of 3.5. We have 21 people in our suburban sample with an average of 6.5 and a standard deviation of 3.2. And then 20 people in the rural sample with a sample mean of 8.0 and a standard deviation of 3.1. And for the hypothesis test, we're going to use an alpha level of 0.01, because we can. Alright, so step 1 in hypothesis testing, as usual, is going to be to write hypotheses. So, as I said before, when you do an analysis of variance test, the hypotheses are going to be the same each time. And you can word them differently depending on what your samples are. But your null hypothesis is always going to be that the population means are the same for each of the different populations that you're interested in. So here we're interested in perceptions of fairness of the police in urban areas, suburban areas, and rural areas in general. And we're imagining, just for the purposes of this class, that we have a simple random sample from each of these areas that we'd be interested in. So our null hypothesis would be that the mean level of perceived fairness in urban, suburban, and rural areas is the same. So in other words, all of the population means are the same. So the extent to which people perceive the police as fair is the same in these 3 different types of places that people can live. Come on. Focus. All right. So our alternative hypothesis then is going to be the opposite of that. So if you rule out the idea that the mean is the same in all your populations, well, you're left with the idea that the mean must be different in at least one of the populations, and maybe more. So our alternative hypothesis could be that the mean level of perceived fairness in urban, suburban, and rural areas is not the same. So as a reminder, this one can be written like this, where it would be like the population mean for urban areas is equal to the population mean for suburban areas, which is equal to the population mean for rural areas. But there really is no equivalent kind of phrasing for the alternative hypothesis. So we just leave it like this. And for these, again, I recommend just write it out in words, because I think that's the best way to accurately portray what the hypotheses are. All right, so step 2 is to find a test statistic. In this case, we're looking for F. And F is the test statistic, so it's a statistic that will calculate based on our samples, that will be able to plot on a sampling distribution, and that will give us information about how likely it is that our 3 samples here came from populations where the true mean level of perceived fairness is the same across all 3. So if people in urban, suburban, and rural areas all see the police as equally fair, what are the chances that you would just so happen to pick 19 people who rated them at an average of 4 from an urban area, 21 people from a suburban area who just happened to rate them at an average of 6.5, and 20 people from a rural area who just happened to rate them at an 8. So it's like, what's the chances of that happening if in reality in the population all the means would be the same? our F-statistic is calculated using that equation that I showed you on the last page, where we're just dividing our mean square between by our mean square within. And again, mean square between and mean square within are values that can be calculated from your sample information here, so calculated from sample size, number of sample, sample size, sample mean, sample standard deviation, number of samples. So all those things go into the calculation. Again, they're sort of a pain to calculate by hand, so I'm not having you do that. But the numbers I'm about to show you, they're not coming out of nowhere. They're based on this information here. And if you guys are wondering when I do these where I tell you that it's just been calculated, I actually plug all this stuff into calculators or programs online to get the accurate values here. So these values will be based on the sample statistics that I have up here. All right, so we're going to say that given this sample information, so given the sample size, number of samples, mean and standard deviation, the mean square between comes out to this. 79.323. Is it big? Is it small? You guys don't have a frame of reference, so we're just going to treat it as a number and go from there. Mean square within is equal to 10.665. And what's really key here is not actually how big or small these numbers are, but how big or small they are in relation to each other. So if you remember, your mean square between tells you, how far apart are each of your sample means, and your mean square within tells you how spread out are each of your samples. So these numbers here describe how far apart these sample means are and how spread out the samples are based on things like their standard deviation. All right, so to calculate this, we just plug these in. So we're going to divide 79.323 by 10.665, and that's going to give us an F value of 7.438. All right, so we found our test statistic. Anytime you find a test statistic, you want to be thinking in terms of plotting it on a sampling distribution. Where here, if you remember, we're looking at an F distribution, where along the x-axis we have possible F statistics, starting with 0 as our lowest possible one, and then going out into higher and higher and higher ones. So our question here, once we plot our F statistic at 7.438, then becomes, what's our p-value? In other words, based on this sampling distribution, how likely or unlikely is it that we would have gotten an F statistic this big or bigger if all of our samples were drawn from populations with the same means? So, like a normal distribution or a t-distribution, an F distribution is standardized, which means that the area under the curve has been calculated for every possible F statistic that you could get. So for any sample statistic, you can look up what that area under the curve is, or you can have a computer program do it. So in this case, as I usually do here, I'm having a computer program tell us what the p-value is that's associated with this F statistic. And that leads us to step 3, which is decide whether to reject the null hypothesis. And so for an F value of 7.438, P comes out to 0.0013. And as a quick note, unlike the t-distribution where you're looking at the area in both tails, an F distribution starts at 0, it has no negative side, so we're only interested in the area that is beyond the F statistic that you got going in a positive direction. So we only want to know the probability of getting an F statistic as large or larger than the one we got. So we're not actually worried about considering the area under the curve on both sides when we're doing an analysis of variance test. All right, so with that, we get a p-value of 0.0013. So the area under the curve here is 0.0013. Our alpha level was 0.01, so our alpha level is larger than our p-value. And this means that we reject the null hypothesis. So based on our samples, we are able to reject the hypothesis that people in urban, suburban, and rural areas all perceive the same amount of police fairness. And more specifically, we'd be able to say that if people in urban, suburban, and rural areas all perceive the same amount of police fairness, on average, the same mean level of So if the mean level of perceived police fairness was the same in urban, suburban, and rural areas, or if people in urban, suburban, and rural areas all perceive the same mean level of police fairness, we would have seen an F statistic as large or larger than the one we got, only 0.13% of the time. So that's our interpretation of the p-value. It's the same interpretation that we have for the one sample t-test and the two sample t-test. The only difference is that instead of saying that we would have seen, a t-score or t-statistic as extreme as the one we got, now we're saying that we would have seen an F statistic as extreme as the one we got. Which is another way of saying we would have seen sample results in which our three samples were as distinct from each other as they were. But I'll finish writing this out before I talk over it. All right, so if people in urban, suburban, and rural areas all perceive the same mean level of police fairness, we would see a sample F statistic as large or larger than 7.438, only 0.13% of the time. So in other words, if the null hypothesis were true, if the population means were all the same, we would have seen samples that were as distinct from each other in terms of their means as these three samples, only 0.13% of the time. So that's pretty unlikely. It's below our threshold set by alpha, where it has to be in the 1% of least likely samples. It's in the 0.13% of least likely samples. So we have enough evidence to reject the null hypothesis and say that there is most likely a difference in perceived police fairness across at least one of these three sort of locations or types of areas. All right, so with that, I'm now going to go back into the PowerPoint and talk about a couple more things related to the ANOVA test, as well as wrap up this means testing stuff that we've been doing.